This is a summary of passive devices that are available to us as analog integrated circuit designers. Obviously, if we're going to be designing analog circuits, passives are going to be useful and very much necessary at times, and it's good to know what sorts of devices we have access to and what their properties are. Let's begin with resistors. There's basically, one primary way that resistors are implemented as passive devices on integrated circuits, and that's using a strip of conductive material, such as is shown up here. Okay, so with a long, narrow strip, it's going to have some finite resistivity from one end to the other, and we can make use of that as a resistor. And the value of that resistor is going to be dependent on the resistivity, the intrinsic resistivity of the material from which the strip is made. So that's this constant sigma here. Sigma is a different constant depending on whether we're using copper or polysilicon or aluminum. And it also depends upon the cross-sectional area of this wire, if you like. So that depends on its thickness here, denoted by the variable h. Okay? So for a given conductivity sigma and conductor thickness h, we get some resistance r sub square here. Now the total length, the total value of resistance for this strip is then given by r square times its length. Clearly the resistance will be proportional to the length of the strip, and divided by its width, right? Because its width, again, is part of the cross-sectional area. The wider it is, if it doubles in width, then the cross-sectional area has doubled and the resistivity per unit length has dropped. Okay, so r square is where this sort of notation comes from, is that you can think of L over W as being the length of the strip normalized to its width, or in another terms, you could chop up this strip into a bunch of squares stacked next to each other, right? And the number of squares that you can draw from one end of this strip to the other is given by this ratio, L over W. And so you can think of that strip as being L over W squares long, and its resistivity, its total resistance then being L over W, the number of squares, times this constant here, which is the number of squares. L over W are things that we control in the layout of the integrated circuit, and of course sigma and h are not. Those are just properties of the manufacturing process. So that's why it's, we usually separate it out this way. R square would be some constant that comes from the manufacturing foundry, and L over W are things under the designer's control. Generally, when you're laying out resistors, you're not going to want to make W very, very narrow. For example, as narrow as is absolutely possible in a given manufacturing process, because doing so will make things like the surface roughness, the edge roughness of the conductor, dominant considerations in the variability of the value of the resistance. So usually you would make it, considerably wider than the minimum that's possible in the manufacturing process, and then, of course, the length would have to increase proportionally to get the same value of resistance. That gives you a tighter control on the resistance. Often you're going to be laying down more than one resistor next to each other, and you're going to be hoping for some matching between those values, so making the resistors a little bit larger helps in that regard too. Now, because all of these conductive layers in our integrated circuit manufacturing processes, whether they're polysilicon or metal or whatever they are, they're all located above a grounded P substrate. Okay, so there's always going to be some parasitic capacitance between the resistor and ground. And since the resistors we just talked about, we're not going to make them very, very, very small, because then we're going to have poor control over their value. So what ends up happening is these capacitors are significant. The area of this strip is significant, and so the value of CR1 and CR2 in the model are also significant. So an appropriate model for a reasonably valued resistor would be something like this. We just often model it as one lumped resistance and some capacitances at either end. Okay. Now if it's a very straightforward layout like this, then we can just presume that, the total capacitance of this structure, we will evenly divide it in the model, and model half of it is showing up at this end and half of it is showing up at this end of the model, so that CR1 equals CR2. So there's some other details here about contacting the resistors that are not being touched on here, but in general you're going to want to consider all of the interconnect that's involved going to and from this strip. That can all be considered as part of the resistor, if you like, if you really need to be that accurate in terms of the value of the resistance. So just to give you an idea for some typical numbers here, R square, it could be in the range of 200 to 2000 ohms per square for a polysilicon resistor. That is a resistance made out of the same material that the polysilicon gates are made out of, except that polysilicon gates have an extra step applied to them where a salicide material is applied in order to intentionally reduce their resistivity. When we're using polysilicon as a CMOS gate, obviously we don't want it to be very resistive, but when we're building a resistor out of it and we want some reasonable values in the range of a kilo ohm or a few kilo ohms or even hundreds of ohms, then most likely we would be we're gonna prevent that salicide from being applied, and we're going to get a larger value of 200 to 2000 ohms per square. Some manufacturing processes will provide special metal layers that are just designed to be useful as resistors. So rather than using polysilicon, we can use these sort of specially designed layers. The good thing is that usually those metal layers are located further from the P substrate than the polysilicon is. So by doing that, we reduce the parasitic capacitances, CR1 and CR2. The downside is that usually any of these special metal resistive layers involves an extra processing step and therefore extra cost. Now, of course, let's not forget that there's another way to build resistors using another conductive strip, if you like, that's actually embedded right in the silicon, and that's simply to use a isolated well region as the resistor. After all, any sort of doped semiconductor material has a certain resistivity, just like the materials we were talking about before. It has a resistivity that depends on its cross-sectional area. Okay, so H here would be the depth of the N-well region within the P substrate. That's what shows up in this expression. And then the conductivity of the semiconductor material depends on carrier mobility there. So in this case, it's an N-well region, so it depends on the mobility of electrons in that doped semiconductor material. And Q is just fundamental electric charge. And finally, Nn is the concentration of dopants and therefore the concentration of charge carriers available in the N-well region. So those factors together give you the value of sigma, if you like, the conductivity of this semiconductor material. It depends on the doping concentration and carrier mobility. And then R square for an N-well resistor like this also depends on the depth of the N-well, or H. Okay. And then we can compute the resistance of this just as we can, with the strip type resistors. It depends on the length, so the distance between the contacts here, and also the width, which would sort of be into the slide here, right? As we wouldn't be measuring the width that way. Some key points about N-well type resistors. Generally, they have a lower resistance per square than polysilicon resistors that are made without the salicide applied. So therefore, they're more useful for making resistors with values in the range of, for example, tens of ohms termination. 50 ohm termination resistors are one typical application of N-well resistors, simply because the resistivity of polysilicon is so high that it would take many, many strips in parallel to get a value of 50 ohms typically. But there are some drawbacks of N-well resistors. They generally have a higher temperature dependence than resistors made out of polysilicon or metal strips, because things like mobility are heavily temperature dependent, and we see that mobility shows up right here in the conductivity of this resistor. Also, one thing you want to notice is that the capacitances CR1 and CR2 clearly depend on the thickness of the isolation, electrical isolation between the resistor, which is up here, and the P substrate. Now, what is providing that isolation? It's a reverse bias PN junction, so there's a depletion region there, whose width depends on the reverse bias voltage applied across it. So, what that means is that, basically the value of these parasitic resistors, CR1 and CR2, depend on the voltages on the resistor. Moreover, if we have some difference in potential across the resistor, labeled here VR, that means that this part of the PN junction is going to have a different reverse bias voltage than this part. Therefore, CR1 will not equal CR2. So there's all of these things pose some problems for analog design. The fact that the capacitance is changing as a function of voltage implies that there's a nonlinearity there, and that can lead to distortion of analog waveforms. Also, the fact that the parasitic capacitances are not balanced may be a problem. If we're trying to use this, across a differential signal path, then both sides won't be seeing the same capacitance. So a couple challenges there trying to use these types of resistors for critical analog applications. So it's usually avoided for those types of applications. But again, the advantages are that it's useful for low value resistors, and also it's available in any CMOS manufacturing process. Basically, there's no extra processing required, no extra cost required. It's always available to you. So that's a good plus. Now let's turn our attention to capacitors. Okay, also very important analog building blocks. You've already seen one type of capacitor that's available to us, and that's simply a MOSFET. Shown here is a NMOS device and its various operating modes. And what you see is that depending on the operating mode, you'll get different values of capacitance. For example, shown at the top is an NMOS device when the transistor is turned off, so the gate voltage is very low. The NMOS device is off, so the channel region here is not inverted. So then, if you're considering the capacitance between the gate and the source, or gate and the drain, you just have this sort of fringing and overlap capacitance, which is relatively small. If you then change the gate voltage so that the voltage becomes positive and greater than the threshold voltage, the channel region will invert, and you'll end up not just with the gate source and gate drain overlap and fringing capacitances, but you also have this capacitance to the channel region, okay, which is now at this point electrically shorted to the source and drain. So clearly what you have is a situation where the capacitance of this MOS device is a function of the gate voltage. Now, that can be desirable in some applications, because what it means is that you can realize a varactor, a controllable capacitor, which can be a very useful block element for tuning circuits. On the other hand, it's not going to be very good if linearity is very important. Again, it's a nonlinearity because the capacitance or the impedance is changing as a function of voltage. It's going to distort analog waveforms, and so that's the problem when high accuracy is important. The way this is usually implemented in practice, a MOS capacitor used as a varactor in an analog circuit would actually be using a PMOS device, not using the NMOS device shown here. Why? Because a PMOS device provides an independent connection to the body terminal. And then by shorting together the source, the drain, and the body all together, they together form one plate of the capacitor, if you like. The other plate formed by the gate. And then what you see is, so you've got now a two-terminal device, effectively, gate and source drain body, okay? And the capacitance between those two terminals depends, as we talked about, upon the voltage between them. Here's a typical plot shown here. So imagine for very large voltages applied between source gate. That means that the gate is at a much lower potential than the source. As a PMOS device, the channel is going to be inverted, and we're kind of in this situation up here, analogous to this situation up here. So we're going to have a fairly large capacitance. On the other hand, let's imagine a very low value, a very negative value of source gate voltage. In that case, the region under the gate will actually be accumulated. So we'll end up with a bunch of charge carriers of the opposite type here. Now in this situation, we have small capacitance between gate and source, small capacitance between gate and drain, but we now have a pretty large capacitance between gate and body. In the case of a PMOS device, since we've shorted them all together here, we again have more or less the same value of capacitance we have when the channel's inverted. But in between those two regions, in between channel inversion and channel accumulation, what you'll actually have, there's no picture for it here, but what you actually have is a range of voltages over which the region immediately underneath the gate oxide is neither inverted nor accumulated. It's basically depleted of charge carriers. So it serves as an extra layer of electrical isolation or insulation between the gate and body. So over that range of voltages, that's the situation here on this plot. Over those sort of moderate source gate voltages, you have a much lower value of capacitance. So you have a tuning curve for this varactor that looks like this. Its capacitance varies as a function of the terminal voltages in this way. Now the model for this device, again, two-terminal device, looks something like this. Now where's this coming from? Well, clearly there's the capacitance that we're interested in, right, between gate and body, source and drain. Okay, that is captured by CMOS, and that's what's being plotted here, right? This is a plot of CMOS versus voltage. But there's another parasitic capacitance between the end well in which this PMOS device resides and the P-type substrate. Okay, that's a parasitic capacitance borne almost entirely by this terminal of the varactor, this terminal of the capacitor. Okay, so that's modeled here by CB. It's a lumped capacitance between basically the body terminal of the PMOS device and the P-type substrate. So this is a good model for that. So again, just to summarize all this about MOS capacitors. MOS capacitors can be used in lots of different ways. Basically, for me anyway, a MOS capacitor refers to just making use of that gate oxide as the isolation layer, the insulation layer between two plates of the capacitor. And you can do that with NMOS, PMOS devices in various operating modes. But regardless, a good thing about it is that you're now making use of the thinnest and most tightly controlled dielectric available in any manufacturing process. And it's the gate oxide. Gate oxides can be, a nanometer, as thin as a nanometer in thickness. Clearly, with a very thin oxide layer, you can realize a high value of capacitance per unit area. So that's a good thing. Provides high density capacitance in terms of farads per meter squared, which means it's cheap because you're not using a lot of silicon area to realize a given value of capacitance. The tolerances on it are reasonable, again, because the gate oxide thickness is such a critical parameter in determining transistor performance. There's quite some effort spent in making sure that value is tightly controlled. So the capacitance value is a reasonable tolerance. And again, if being used in a tuned circuit, like for example an oscillator where you want to have a tuning knob to control the oscillation frequency, the fact that its capacitance varies as a function of voltage can be thought of as a good benefit. On the other hand, it can also be very undesirable if you're applying signal swings across of it that's causing the capacitance value to vary, and then introduce nonlinearity and distortion. That can be a bad thing. Also, in modern CMOS processes, the gate oxide is so thin that there's a considerable amount of leakage across this capacitor. That can be a problem. The parasitics associated with this capacitor can be large because we're talking about a well to substrate depletion region capacitance. Also, they're imbalanced, so the parasitics are borne mostly by one side of the capacitor. And finally, there's not shown here in this model, but recognize that one side of this parasitic capacitance, CB, is connected to the P substrate, and the P substrate is generally quite lightly doped and therefore has quite a high resistance. That can lead to loss and basically heating in the substrate and therefore energy loss in your circuit. So that can also be a problem. Now some of these problems can be addressed by clever configurations, and in any case, MOS capacitors are certainly very useful. If nothing else, they're very useful as decoupling capacitances between supply and ground. Um, Unless you're really worried about the leakage there, they're going to provide you the highest capacitance per unit area on your chip. Now, if that's not suitable, if what you really need is a nice linear capacitor, then usually what you would use is some sort of metal and metal capacitor. I'm using this as a very general term to denote capacitors made out of two conductive layers above the semiconductor substrate in an integrated circuit. So the simplest, most obvious way to do it is, to just put two sheets of metal next to each other, and then you get a classic parallel plate capacitor. Um, Notice in this case, again, as always, there's parasitics to the silicon substrate, so that can be modeled as parasitic capacitances to ground. And in this configuration here, you've got, again, an imbalanced parasitic capacitance. The bottom plate will have more parasitic capacitance to ground than the top plate. Um, this could be a problem if you're trying to use it as a differential capacitor, but you can always address that by just splitting the capacitor in half and connecting them in anti-parallel so that that way the parasitics sort of balance out. Um, on the other hand, sometimes this is actually a very good advantage. Imagine if you're going to be using this capacitor so that one end of it is grounded anyway, connected to a small signal ground anyway. Well, then what you do, imagine this terminal is grounded. Well, you just make sure that this is the bottom plate of the capacitor in the layout. So the fact that it has huge parasitics makes no difference because that plate's grounded anyway. What you're doing then basically is you're having a capacitor where one of the plates has a low parasitic capacitance and you're making sure that that one is on the critical network. This is a very common trick that's used in analog circuit design and very nice and beneficial. This terminal here, for example, might be not necessarily connected to a ground potential. It could be connected to a supply voltage, could be connected to the virtual ground terminal of an op amp. Again, similar advantages apply since that node is not going to be moving up and down very much. Might be okay that it has a higher parasitic capacitance to ground. Another way to make capacitors out of the metal interconnect layers above the substrate is shown here on the right. This is an interesting technique that's become very popular now in scaled, very small feature size CMOS technologies because the interconnect can be made with such fine pitch that actually the wires themselves, if minimum width wires are looked down upon from the top, they actually look like this. They're sort of these bars on edge. They're a lot thinner than they are sort of tall. So it makes sense at that point, and also they can be jammed very close together, packed very close together. This is of course important for digital routing applications. We can make use of it in analog design by recognizing actually the sidewall capacitances obtained by jamming a bunch of these wires next to each other can be very high, and you can get a higher capacitance per unit area using a structure like this, it turns out, using the sidewall capacitances, than you can with two parallel plates like this. So of course if you want a two-terminal capacitor, you would just somehow short together alternating layers. And of course both these approaches, we can increase the capacitance density further by stacking these on multiple layers. A typical modern CMOS process might have 6 or 8 or even 10 layers of metallization above the substrate. So you could use, 4 or 6 of those layers for capacitors if need be, and just stack these structures one on top of another and get a higher density. So regardless of which approach you use, again, some pros is that these capacitors can be made symmetric. Um, they provide a capacitance that's very linear. Okay, there's no depletion region that's changing as a function of voltage or anything like that involved here. So they're very linear capacitors. And you at least have some control over the parasitics in that you can decide what layers of metal to implement them on. So you can make them have low parasitics by using high metal layers, um, or you can make them have a very high capacitance density by stacking layers on top of each other. So, so these are, again, the most common types of capacitors used for sort of critical analog signal path applications. The cons of them, well, they're just a fixed capacitance, so they can't be used as a varactor. Um, uh, on their own, of course, what's being done now is just r- implementing an array of these all next to each other with switches in series, so you can turn individual capacitors on and off, and thereby you get kind of a digital varactor. So that's being done, but one individual metal capacitor on its own is not a varactor, and because the oxide layers that separate neighboring conductors are not as thin as the gate oxides, which again can be as thin as a nanometer or even less. So the capacitance density is typically not going to be as high as using a MOSFET. Now, in fact, in modern processes, these capacitors can have a capacitance density almost as much as a MOSFET because you can stack so many of them on top of each other. Now, if you want, there's no reason why, if you really need super high density, you couldn't just stack a metal capacitor on top of a MOS capacitor and put them all in parallel and realize the highest capacitance density per unit area. That's certainly a viable approach, again, if you're just using it for decoupling or something. Another thing I want to point out as well, final thing, is that as with resistors, depending on the particular manufacturing process, some will have special layers available that are there for no other reason other than to implement high density capacitors. For example, what used to be popular was having a second polysilicon layer just above the main gate polysilicon layer, again separated by relatively thin dielectric. Now, polysilicon is not used as often as some other layers that are higher up in the metal stack, providing lower parasitics. So when available, those obviously provide a very good alternative, but of course come with some extra cost. Um, Another general point, regardless of what type of passive devices we're talking about here, whether it's capacitors or resistors, is that just as with transistors, whenever matching is important, we're going to want to realize our passive devices made out of a sort of fixed library of unit-sized passive devices. And we're going to want to make up all values that we need in a circuit out of either series or parallel combinations of these unit-sized devices. So for example, if it's a resistor, we might have a 5K resistor that we've characterized. We understand its parasitic capacitances and what the model for it looks like, and we're going to build everything out of those 5K resistors. If we need a 50K resistor, we're going to put 10 of them in series. If we need a 2.5K resistor, we're going to put 2 of them in parallel. Okay, that going to give us good matching and good consistency in our modeling. So again, just as with transistors, don't assume that you have, infinite control over the precise value of these components. Also, another important point to make is that the tolerances on these values, whether it's capacitance or resistance, is not going to be on the order of 1% or 2%. It's more likely to be in the range of, 10%, plus or minus 10%, or even higher, plus or minus 20% on these values. For example, resistors, especially, have a temperature coefficient associated with them. Any material's resistivity depends to some extent on its temperature, and so the value is going to vary over temperature. The value is going to vary from one process to another. Lithography inaccuracies may cause one resistor to have a little bit thicker trace than another one. So it should not be assumed that the precise value is very well known. For capacitors, the problem may even be in the modeling. You may not be accounting for every fringing field that there is there. So you've always got to allow for quite some variability in these passive component devices. On the other hand, if you're making these passives, again, you're making sets of them out of the exact same unit size devices, what you can rely on is good matching. So matching on the order of 1%, for example, is not unreasonable. So finally, the other passive component we haven't talked about yet is our inductors. Inductors is certainly possible. It can be implemented in integrated circuits just by spiraling metal. As is shown here, there's actually a dye photograph showing several spiral inductors connected in series. Now, of course, there's no magnetic core there, which is a bit of a problem and makes the values of inductance that can be realized on chip quite small, relatively small, in the order of nanohenries. Um, but still, there's RF applications where these are very, very, useful and commonplace. Uh, but it's just going to be outside the scope of this course, so I'm not really going to dwell on it.